Vector addition is pretty straightforward, and we've learned this before. As a quick reminder, if we have three vectors, blue, purple, and red, the way we add them is by connecting them tip to tail. So it doesn't matter which one I start with. I'll begin with blue. At blue's tip, I connect the tail of purple. Then at purple's tip, I connect the tail of red. And once we're finished, we go back to the original tail and we draw a new vector, the resultant, that points from the original tail to the final tip. It's tail to tail and tip to tip. And the cool thing is it doesn't matter what order, it doesn't matter what order we add these vectors in. If we had started with red first, blue second, and purple last, look, the resultant, tail to tail, tip to tip, is the same as before. So you can do this in any order, purple, red, blue, and as long as we add correctly, tip to tail, the order in which we add does not affect the resultant. When it comes time to do subtraction, here's how that process works. We say, okay, find the displacement, which is our final minus our initial. But here's what we do. We rewrite the subtraction as addition. All we need is negative our initial, and we add negative ri with rf. So here's rf, here's ri. What does negative ri look like? It's the exact same vector, but the tip is on the other side. So let me take rf and negative ri, and when I add those together, when I add tip to tail, right, adding means connect the vectors tip to tail, the resultant in black is tail to tail and tip to tip. That's the delta r vector. Now, if you look back at this original picture, there's another way to think about subtraction. Delta r, you could take this and add ri to both sides. And if you want, you could say, you start at the initial vector, and then we have to add some change that takes us to the final vector. And the change goes from the initial, it takes us from the initial and makes rf the resultant. So this is another way to think about it. If you like this method, you can do that. Otherwise, you can simply say, okay, impulse j, j is the same as change in momentum. So j is the same as final momentum minus initial. That's tricky. Okay, so take the final, here it is. And then we need negative pi, the initial, so here's pi. Let me make it negative by putting the tail on the other side. Then I take those vectors, I add them tip to tail, like this. And I draw the resultant, which is tail to tail and tip to tip. There's delta p, which is the exact same as j, the impulse vector. That's how we do these problems. We'll do a few, pause the video, try them on your own, and then we'll do a few more here. Okay, here we go. Here are some more. The change in momentum is final minus initial or plus negative initial. And if I add final, if I add final here with negative initial, what does that look like? Looks like it would kind of point off to the side, tail to tail, tip to tip. There's delta p. I'll do these last two. Here's v final, that's negative vi. And if I add those tip to tail, again, I'm doing vf plus negative vi, and vf minus vi, or vf plus negative vi, gives the change in velocity. How about this one? Draw the relative velocity, the velocity of b with respect to c. To do this, we have to remember our relative velocity rules from way back in Unit 1, or Unit 2 maybe, in Honors Physics. So the rule was match up the subscripts so that these match there, and the inner subscripts kind of are the same. Cancel out, can we say that? Well, not really. But the point is, we need an equation. We're looking for VBC. To isolate VBC, we subtract VAB from both sides. And now we see we need to take this guy, AC, and add tip to tail negative AB. So here's negative AB. There's AC. There's negative AB. And the resultant is BC. So again, here's what we did. We took VAC, we added with it negative VAB to get BC. All right, that's how we do vector subtraction. Thanks for watching.